The world of quantum physics has just witnessed a groundbreaking discovery that could reshape the future of quantum computing and spintronic devices. Researchers have achieved the remarkable feat of creating magnetic graphene that exhibits the quantum spin Hall effect without requiring external magnetic fields, a breakthrough that eliminates one of the most significant obstacles in developing practical quantum circuits. Graphene, the revolutionary two-dimensional material made of carbon atoms arranged in a honeycomb lattice, has long captivated scientists with its extraordinary properties. When modified magnetically, this wonder material becomes even more transformative, opening doors to unprecedented applications in quantum computing and advanced electronics. What's going on here, John?
Yeah, so these scientists at Delft University, I think that's it. So they've created quantum circuits that work without these massive expensive magnets. And they did this by layering graphene on top of a special magnetic material called CrPS, which means that we could have ultra-thin quantum devices that are smaller, faster, and more practical than anything we've ever seen. So why does this matter? Well, think of it like finally being able to build a supercomputer that fits in your pocket without needing a refrigerator-sized cooling system. Because, for those of you that don't know, current quantum devices need huge magnetic fields and extremely cold temperatures to work. So this discovery shows we can get the same quantum effects at much warmer temperatures, though at this point, it's still not quite room temperature for the quantum effects, but also we don't need it without external magnets. So the quantum spin Hall effects, or QSH, I think we've covered it before. It represents a topological phase of matter where electrons flow along the edges of material in spin-polarized helical channels. So in this study, the researchers achieved this by creating a van der Waals heterostructure where the monolayer graphene is placed on the CrPS, which is chromium thiol phosphate, which is an interlayer antiferromagnetic material with a Néel temperature of approximately 38 Kelvin. Okay. So the substrate induces both staggered potential and spin orbit interactions within the graphene through proximity effects. So the engineering essentially fundamentally alters graphene's band structure, and that's what opened the topological gap in the bulk while preserving the gapless helical. I always have a hard time with that word, edge states. So super cool. Love that they've got this. What are your thoughts on this? Do you think we're on a path to having a quantum computer every household?
Well, now that they can put this on chip, I'm trying to understand how electrically charged graphene can create this spin Hall effect in the chip. So it's just, I'm curious to see how all of that is going to work. Yeah. But this is very interesting. We've long heard graphene, that it's the future of everything. Like, it's the new wonder material that can do almost anything. And I love to see it being put to practical use, but I want to see this actually coming out of the lab and being used in other things. But being able, not having to have that external electrical magnets, which is heavily cost from electricity point of view, and being able to run these operations at room temperature is, again, it brings the requirement way down. So we definitely are closer to quantum computers everywhere. And what does that mean when every laptop's a quantum laptop?
Yeah, I can't even begin to think what that means for the general public. I can't even though we've covered quantum, so much quantum computing, so much quantum physics, I still can't wrap my head around what would that mean for someone like you or I to have a quantum computer on as a laptop. Can you?
No, because in my mind, I've always thought these quantum computers were closely guarded governmental or major, multi-billion-dollar corporations holds them secretly. They're in one of those sci-fi centers that you got to walk across this catwalk to get to, that's super secure. Yeah, I've never imagined it being in a laptop where everyone can run around and do their own things, but we are getting that way too. For example, I never really imagined AI would just be in our laptop. And I've seen some sci-fi ages ago where I think there was some traveler from the future who had a computer the size of a credit card or something that he traveled with. That was a fully AI thing that could do stuff with them, but that was, from the future. And so now you sit back and say, now we're doing personal AIs, we're doing all sorts of stuff that are local, or we're training them ourselves and doing that. The future is high powered. It looks like quantum computers with our own personal AIs running all sorts of stuff and working together. It's a fascinating, scary, and wonderful looking future when we start looking at this technology and what it means when we can start doing quantum computer at room temperature.
Yeah. So a couple of things. The quantum effects, they still require cryogenic temperatures. So the room temperature aspect refers only to the Hall effect, right? The real breakthrough in what we're covering here is that it's eliminating the external magnetic fields, not achieving room temperature quantum effects yet. And so the next challenges that they're going to be facing is fine-tuning kind of the spin orbit interactions, minimizing disorder, and then obviously scaling up for practical devices. So there's a lot of integration opportunities here, like you were talking about, combining this advancement with existing semiconductor technologies. And there's a potential for creating more stable qubits and quantum logic gates by doing this. So I think this is a huge advancement. I don't know if we talk too much about spintronics and stuff. So like traditional electronics, the way that they work is they use the charge of electrons to process information. And I like the word using spintronics because it talks about how quantum works more. Spintronics uses electron spin as opposed to just the charge of a 0 and 1, if that makes sense. So I like that. There's a lot, and I know we're covering a lot of quantum, but there's a lot of quantum advancement that's happening in the last year as opposed to the last 5 years, if that makes sense.
Yeah, it's really coming along. We've been doing this for a couple of years now, and we had a handful of quantum articles randomly come along at the beginning, but it's more and more almost every week. There's new quantum breakthroughs, and we're really changing. This is taking leaps forward, and we're really going to see, I think, some big changes in this. And that scares me a little bit because as we think we're ready for quantum, like we talked last week about RSA being broken by quantum.
Yeah.
And that looks like it's going to be 20 or 40 years away, but yet we're taking huge leaps forward with stuff like this. And I wonder, is it really that far away?
Yeah, like as these advancements come out, I think that timeline is shrinking as far as getting a practical room temperature quantum computer, because this work represents a first in demonstrating the Hall effect in magnetic graphene without external fields, which is if you think about it, it's part of a larger global competition between IBM, Google, and other startups who are pursuing different approaches to practical quantum technologies. And so this proximity engineering approach that's demonstrated that we're talking about, it could provide an actual manufacturing advantage by being compatible with existing semiconductor fabrication techniques. And I know I kind of touched on it, but I just wanted to link those two together because that's huge. That's another big advancement, is being able to link it to current manufacturing techniques, which will help to scale and commercialize.
Yeah, so the research priorities need to focus on scaling manufacturing processes for larger magnetic graphene devices, improving interface quality across multiple layers, multiple material layers, developing a standardized fabrication techniques, and creating hybrid systems combining multiple quantum technologies. I'm really looking forward to where we're going with quantum, and we're going to continue to cover it and talk about these things. We'd love to hear your feedback on this magnetic graphene. What are the other practical applications for it other than quantum? And what are you looking forward to? We'd love to hear from you. So, what do you got going on, John?
Yeah, so coming out end of September, definitely gearing up for Elevate. I know you're a partner with Elevate, aren't you, Craig?
Oh yeah, absolutely. So definitely we'll be doing something during the Elevate a week, probably a flowgrammer event, if nothing else. They're a partner of ours. Definitely go out and check it out. There's a lot of great events going on related to Elevate. That's why I said great events, sessions, program. Check out their schedule. Check out all the different lines of programs and stuff. There's always good things there. So definitely go check out Elevate. And check out Toronto Starts for our startup drinks, our startup investor drinks, and our flowgrammer events where we help people learn how to automate things in their business. And John, if people need funding, where do they go?
Yeah, come find me on LinkedIn. I just posted some news about the Shred program, but come find me on LinkedIn, send me a message, and we'll set up, we'll talk and see if it makes sense to find some non-dilutive funding for you.
Really appreciate everyone taking their time to watch or listen to this week. We'll see you again soon.
Thank you.